Okay, we're discussing projectile motion and how when you release the object from a height h at an initial angle theta and initial speed v naught, then we have the formulas that are in the boxes here for the acceleration, velocity, and position vectors. Now through physics we have other formulas that we could use, and so we find out that if you ever need to find the maximum height, there's a formula that you can use. This is given in the textbook, but the problem with this formula is that it's based off of the fact that it's launched from the origin. So what that means to you is that that initial height that we had in the other formulas is equal to 0. Okay. And so, yes, it still has the initial velocity. Yes, it still has the launch angle. They call it alpha here. It still has the initial speed. And we have the launch angle called alpha in these formulas. But here are the formulas now. We have the maximum height reached by the projectile can be found by this. If h is not 0, then all you do is, you just adjust for it. You say, well, y max is the formula on this right hand side here plus h. And so the max height, let's call it max height. So max height will be the y max from this formula here plus the h. Now that you're able to recover that. These other two guys though, flight time t and range r, we can't recover and just add something to get them, and so they are totally based off of the height being set equal to 0. But if you have height set equal to 0, we can find the total flight time by plugging into this formula, and we can find the total range, basically this distance that the horizontal distance that the projectile covers by this formula. So we have the range is the initial speed squared over g, the gravitational constant, times the sine of twice theta. And the time in flight is twice the initial speed times the sine of alpha over that gravitational constant. And we can use this to answer questions. So let's take the next slide. We're going to be firing golf balls. This is a question from the textbook. Okay, so a spring gun at ground level fires a golf ball at an angle of 45 degrees. So that tells us that alpha in those formulas is 45 degrees. Now, there it is, ground level, so h is 0. We can use all the formulas. The ball lands 10 meters away. That 10 meters is the range. And be careful with the units there. Now, since we're in meters, then when it comes time to consider the gravitational constant g, then we have to use the metric version of it, which is 9.8 meters per second squared. Okay, so the question at hand is, what is the initial speed of the ball? Well, we have that formula that says that the range of the ball is the initial speed squared over the gravitational constant times the sine of twice the angle. Well, we have everything but the initial speed. Plugging in, we'll have 10 is equal to the initial speed squared over 9.8 times the sine. When you double 45, you get 90 degrees. And the sine of 90 is just 1. And we can solve this for initial speed squared. We'll have multiply both sides by 9.8, and so we'll get 98 is equal to initial speed squared. Okay, and without a calculator it's kind of tough, but we can do it. We take the square root of both sides. The square root of 98 is this initial speed that we're looking for, and that has a perfect square as a factor, and so we say that this initial speed is 7 root 2. It's 49 times 2. We can pull out a 7. The units, well, it's a speed, so it's in meters per second in the metric system. Okay, and that's the answer to part A. Now part B, it's a little more involved. In part B it says, okay, for that same initial speed, so when V naught is 7 root 2 meters per second, find two firing angles that would make the range equal to 6 meters. So I want to fire the golf balls at 7 root 2 meters per second, and I want the range to be 6 meters. I want the ball to fall 6 meters away. The question is, well, what are the angles? We just go with the same formula. Gravitational constant, once again, is the 9.8, and we just solve for alpha. Okay, so we have that 6 is equal to 7 root 2 squared over 9.8 times the sine of twice alpha. And we can go find out what alpha is. Okay. Now, 7 root 2 squared is exactly 98, right? Back to over here. So we have 98 divided by 9.8. Okay, and so that's just 10. And so we have 6 is equal to 10 times the sine of twice alpha. Or that the sine of twice alpha is equal to 3/5, reducing. Sorry about that. Okay, so then the arc sine both sides, and we'll have twice alpha is the arc sine of 3/5. Now, at some point we'll need to go to a calculator to get the answer, but what happens is that we get one answer, and then we can also get its complement. The way the sine of twice alpha works, the sine of twice alpha, or any angle, sine of twice any angle, is 2 times the sine of the angle times the cosine of the angle. And when you have complementary angles, this product will always be the same. The sine of the angle times the cosine of the angle will be the same. And so whatever we get for alpha, when we divide by 2, it turns out to be approximately 18.4 degrees. But we also can get the complement of that, 71.6 degrees. It's because this product, sine alpha times cosine alpha, would be the same as the when you use beta as well, because the way complements work, we have the sine of beta being the complement of alpha, cosine of beta. Okay, they just flip-flop. The sine of beta is the cosine of alpha, and the cosine of beta is the sine of alpha. And so that product will be the same, so it'll still be true for that. And so these are the two firing angles. If you fire at 71.6 degrees, or if you fire off at 18.4 degrees, it'll land 6 meters down the road.